So last time we talked about the Poincare-Bendixon theorem. The Poincare-Bendixon theorem is a theorem that allows us to prove what? Wilson? Allows us to prove what? Krista?
I was in here.
Okay. What is it good for?
There's a existing cycling thing.
Actually, a little bit weaker than that. It allows you to prove the existence of oscillations, periodic solutions. Periodic solution. Theorem that allows to prove existence of periodic solutions. Okay. Now, there's many ways to state this theorem. One of the, like a simple way to state it, although I understand it's a little bit subtle, no matter how you write it. But suppose that you have a solution of a dynamical system in 2 dimensions. And you know that solution is bounded, so it doesn't blow up to infinity. And you know that it doesn't approach one of the steady states. It stays away from the steady states. So it must do what? It must approach a periodic solution. Or it must be a periodic solution. In either case, there must exist a periodic solution. Right? Fair enough, right? So if we have a situation where we have a set that does not have any steady states, or that the steady states that there are repelling, they push away solutions, then you have the situation, right? You have these solutions that are bounded and stay away from the steady states, and therefore must either be a periodic solution or approach a periodic solution. Okay? So the way that we're going to use this in practice is through the following theorem. You got your dynamical system, and suppose that there exists one of the following. Either one, a bounded set D with a single repelling steady state. By the way, and this is in 2 dimensions. And this is also in 2D. There are generalizations for 3D, but for n dimensions, but they're not that general, and we're not going to talk about them today. So suppose that there is a set, bounded set, that has a single steady state, and that single steady state is repelling. Repelling means, unstable spiral, unstable node, one of those things. It pushes away the solutions. Okay? And such that solutions that start in D stay in D. So, like Las Vegas, right? All right, bad joke. Anyway, so you have only a single steady state, okay? And that steady state is repelling, and the set is such that the arrows in the edge or the boundary of D push towards the inside of D, right? So that means that you can never get out of D. If your solution starts here, it must stay in there. Okay? And that steady state is repelling. So either that or a set that is an annular set, D with no steady states And then the same thing, such that solutions in the stay in the set D. And then you can imagine this like this. It's some kind of donut, an annular region, such that the edge, vector field at the edge, is pointing towards the inside. And because this is part of the whole is not part of the set, we also need to have this situation here. So this is D. Okay? Suppose that you have either of those situations. Then what? What's the conclusion of the theorem? Then there exists a periodic solution in D, right? Then there exists a periodic solution in D. All right. Why does it exist a periodic solution? Because of the Poincare-Bendixon theorem, the way that we stated it. If a solution is bounded, so either of those sets is bounded, and stays away from the steady states, which it must in both cases, then it must either approach a periodic solution or it is a periodic solution. So in both cases, you can conclude that there is a periodic solution, which is what we want to prove. Okay. Now last time, I gave you an example of such a set, and I was not entirely happy about it because it's a little bit hand-wavy. You know, like it wasn't entirely clear why this annular set worked. So today, we're going to be a little bit more rigorous, and I'm going to try and do a set of this type, okay, that we can see more clearly, and that therefore implies the existence of a periodic solution. Okay, so the example that I'm going to talk about is the Schnackenberg system. I like the name already. So Schnackenberg is a chemical reaction that presumably is oscillatory, right? We would like to prove that it's oscillatory. So we talked about this last time from the 1970s, I think. Do you guys remember we talked about this system already? When did we talk about this system? Well, we talked about this system when we talked about Hopf bifurcations. Okay? This was a system with the following reaction equations. So you have 2x plus y goes to 3x, and then you have the reaction that nothing goes to y. So y is produced is produced in the system at a rate a, and x gets destroyed. Okay? We derived the equations for these things. When there's nothing on the edge, we assume that there's a 1. So we can just recall the differential equation. What was that again? This is the hardest one. 2x plus y goes to 3x. So x is being produced, right? So the reaction is x squared times y, okay, with a plus 1, if you will, because the stoichiometry is 1. And then there is a minus x, because x is getting destroyed here, okay? And now y prime is equal to minus x squared y, because you see y is getting destroyed in this reaction, plus a times y. No, sorry, plus a. Plus a. Okay. And it's so well and good to write this down intuitively, but if you really want to make sure you're doing it right, it's worthwhile to write it in terms of the stoichiometry matrix and write it as a product and everything. That way you make sure you don't make any mistakes, like I was about to do. So there you go. That's the system. And we proved that this system has a Hopf bifurcation. Okay? Now let's try and do the same thing using Poincare-Bendixon theorem. Okay? By the way, if you might remember, we didn't actually prove that one completely. If you remember, part of the Hopf bifurcation argument requires you to look at the case where A is equal to A0, the critical value, and prove that that system is stable. And actually, we didn't do that. We kind of waved our hands and we said, well, you know, you just look at a computer, whatever. So that was not a completely kosher proof either, right? So today we're going to try and fix it to make it a completely kosher proof that there are oscillations in the system. Okay, now let's look at the system and figure out the null claims. So the null claims, the X null claim was what again? The set of points where x prime is equal to 0. So 0 is equal to x squared y minus x. So x is equal to x squared y. Okay, that means that either x is equal to 0 or 1 is equal to x y, right? Okay, and this means that y is equal to 1 over x. All right, so there you go, that's the x null claim. Now let's look at the y null claim. The y null claim is a is equal to x squared y, or y is equal to 1 over x squared. Okay, let me try and draw this. Do some kind of null claim analysis here. This is x and this is y. And I'm going to start with, let's say we start with this guy here, 1 over x squared. Okay, this is x prime equals 0. That means that the arrows are horizontal or vertical? Vertical, right? Okay. What about, there's also this other set here, right? X equals 0. Those are these points over here. So over here, the arrows also should be vertical. Right? And here the arrows are also vertical. Okay? What about the other null claim? The other null claim is just 1 over x squared, right? And that one looks like more or less like this. And the arrows are horizontal, that's right. Okay, now let's evaluate this at certain points. For example, at the point 0, 1. Point 0, 1, this is 0, and this is 0 plus a. It's positive, right? Okay, so these guys are pointing up. All right. What about, say, let's say over here. What point is there that is over here? So the point, no, the point 1, 1 is, I think, is going to be on the, right? So evaluate, let's say 2, 1/2. Okay? So x prime is equal to 2 times 2 squared divided by 2 is 2 minus 2 is equal to 0, which is not surprising because we're on the x null claim. And y prime is equal to minus 2 squared times 1/2 is equal to minus 2 is negative. Okay, so it goes which way? Goes down. So these guys go up. Okay, now let's evaluate at one of these points over here. For example, point 2, 1/4. Okay? So y prime should be equal to 0 because it's on the y null claim, and x prime is equal to 2 squared times 1/4 minus 2 is equal to 1 minus 2 is equal to minus 1 is negative. So that means that this arrow is pointing this way, and these arrows are pointing this way. Yes, Wilson?
I was wondering, where did the A go in both of the Y's prime?
Where did the what go?
The A? When you plugged it in.
Oh, you're right. You're right. Oh.
And also over there, it just turned into 1.
Wait a minute. Where did the A go? You're right.
Y is equal to A over x squared.
I see. I see. Okay. So I guess we should multiply this by A. So in this case, it doesn't really matter. But in the case of the Y, we should do something like A over 4. Okay? So thanks. So this is 2 comma A over 4. And this is... So this is 2 squared times A over 4 minus 2.
Do that to the first one, because there's no A in the x prime, but there is an A in the y prime.
Okay, let's do it with this one first. So this one shouldn't matter too much because we're on the. Yeah, let me just do this one first. So this is 2 comma A over 4. So this is. It works? Okay, so where should I fix here?
It should just be A minus 2.
Minus 2A? No, minus 2?
Yeah,
A
this one.
minus 2.
Plus A minus 2. Okay, so this is A plus, no.
Just A minus 2.
Yeah, but how do you know that's negative?
We don't know that that's negative.
Minus 2. All right, then let's make A small and positive, okay? I'm not sure, I may have made a typo here. So, so if this is equal to, Jesus, okay, so this is, yeah, let's do it right. Minus, minus x. This is equal to A minus 2. Okay. All right, fine. Let's assume that A is less than 1. Okay? All right. So this is less than 0. All right, fine. And now to go back to the other one that Wilson suggests. The blue null claim is still 1 over x, right? Right? So this point is still supposed to be on the null claim. So this value should still be equal to 0. And is it equal to 0? Yes, because if I evaluate this point here, it's still 0. Okay? Now, at this point, we actually should make a change because this is minus this plus A. Okay, it's equal to minus 2 plus A.
Which is the same.
Same as before. Okay. Okay, thanks, Wilson. Awesome. All right, so, all right, let's restrict ourselves to A small, A less than 1. All right, so now, so now the question is, can we build a region D that satisfies the assumptions of the theorem? And specifically, I would like to focus on this kind of region. annular, the one with the one single steady state that is repelling. Okay, so ideally I would like to make some kind of square around here, or some kind of region here, such that the arrows are pointing in. But you see that's not easy, because you see the arrows are pointing over here this way, they're kind of getting out, right? Over here, I have no guarantee that this is working, because the arrows are pointing somewhere in that general direction. And over here, somehow they're pointing down, but I'm not sure. I'm not sure how to build this region. In fact, it's not easy to build it, and you cannot really build it. At least it's not clear how to build it, okay? So what Schnackenberg suggested is a slight change to the system so that this part of the argument works. Okay, are you ready? So we're going to change the system slightly, okay, to fix that situation and so that it works. Okay, so new system is we have now 2x plus y goes to 3x. This goes to y, and x goes to 0. But we're going to assume that x can also get produced. And it can get produced at a rate equal to b. Okay, so it's a slight change. Doesn't change the chemical reaction very much. And let's look at the new ODE system. So the new ODE system is very similar as before. Okay, so the new ODE would be x squared y minus x. Let me just write down what we had before. Plus a. Okay, and then what else should I change here? What is different now? Plus b, right? Okay, you agree? Great. All right, so now let's look at the new. Let me write this down. The problem here is that it's not clear how to define the set D. Okay. Now we're going to do the new null claims. The x null claim is now, let's see, x squared y is equal to x minus b. So y is equal to 1 over x minus b over x squared. And the y null claim is still what it was before. Y is equal to a over x squared. So this is the old null claim, and this part is new. Okay, so now let's think about it. How do the new null claims look like? So let's see, the red null claim hasn't changed. I'm going to still draw it the same as before. What about the blue null claim? How does this function look like? 1 over x minus b over x squared. Well, again, we can spend some time doing calculus 1 on this function. But basically what it is you take the function 1 over x, the function 1 over x, and you subtract, this is 1 over x, and now this is the function minus b over x squared. Let's think about b some small number, for example. Okay, so you're taking this function and you're bending it down. These values, by the way, are, I'm going to exaggerate things a little bit. These values are very small, and these values are very, very large and negative, right? More large and negative than these ones, right? Because x squared, 1 over x squared is bigger than 1 over x for small x, right? So when we add these two functions, what happens around 0? What do you think happens around 0?
Negative.
It goes negative, right? It goes to negative infinity. And then it goes up, and then it goes down again, right? So it's essentially it's like we're taking this function and we're bending down this curve over here. Okay? Again, you can do this with calculus, you know, more properly, whatever. But what you're gonna find is that it looks more or less like this. This is x prime equals 0. Okay. Now, the details, the algebraic details change, but it's essentially the same thing. We're just bending this curve a little bit. We're not changing the values of the vector field elsewhere very much. And so in fact, you can do the same argument as before, and you get the same directions of the arrows. You get these arrows here. You get these arrows here. And you get these arrows here. All right. So now something really cool happens. Imagine that I draw the following rectangle. I'm going to go at this tip over here. I'm going to go down. Then I'm going to go to the side until here. Then I'm going to go up like this. All right? All right. Now, what happens at these arrows over here? Well, you see, the system is going around, you know, over here they're pointing down, over here they're pointing there. So in this direction, they're actually pointing like this. Okay? Over here, the arrows are pointing this way. Okay? Over here, they're always pointing that way. And over here, they're pointing that way. So it's like this, right? Like in the theorem. It's a Las Vegas set. Actually, I hadn't thought about that, but anyway. Solutions that start there, stay there, right? Okay, fine. So now we have one of these sets no matter what. What we would like to show is that this steady set is repelling, right? Because we don't have that yet. Okay? But do you guys agree with me that this shows that this set is, you know, what's, you know, if you start there, you stay there, right? Okay, awesome. Great. So now, we only need to prove that the steady state is repelling, for instance, unstable spiral for some values of the parameters. Okay? Now, once again, you know, you can do it as detailed as you want. I want to spare you the details, but basically what this involves is calculating the steady state, calculating the Jacobian, evaluating the Jacobian at this point, and finding the eigenvalues, right? And then you find under what conditions for A and B you have eigenvalues that have a positive real part, that are complex and have positive real part, right? Okay, so let's do this, not in too much detail, but let's do it. So I'll do it over here. So to do this, we need to calculate eigenvalues around, eigenvalues of the linearization around steady state. Okay. Now you can actually solve this system of equations to find the steady state. You'll find that there's only one steady state and has the form or the value a plus b comma a over a plus b squared. Okay. Now you can calculate the Jacobian around this system. In fact, we may have, no, I don't think we did it already for that system, but it's very easy, right? What is the Jacobian? Anybody wants to try? Jacobian of this system. Actually, where is here? Okay. So who wants to try? Natalie?
So the first one would be
Let me write it over here.
2x
Oh.
minus 1.
2x,
Oh, 2xy.
2xy minus 1. The second one is
X squared.
x squared. Then
Negative 2xy.
okay, and here
That one's going to be negative x squared.
you got it. Okay, so what happens when we evaluate it over here at those points over there? Well, we just get we have to multiply, right? And 2xy minus 1. I guess it needs some algebra, but you can get to this expression. Okay. All right, so again, this one right here needs some algebra. These ones I think are okay, no problem. How do we get here again? Minus 2a over plus b. No, that's fine. Minus 2a multiplied, so this times 2. It's this right away. Okay, fine. So, so now, what conditions do we want on the eigenvalues? What would we like the eigenvalues to look like? We want them to be here, right? Okay. So now let's try and find conditions on the trace and the determinant that guarantee this situation. So recall, in an arbitrary matrix, if the matrix looks like this, A, B, C, D, right? The equation to determine the eigenvalues is A minus lambda, B, C, D minus lambda is equal to 0, but this is equal to A minus lambda, D minus lambda, minus BC equal to 0, and this is the same thing as lambda squared minus A plus D lambda plus AD minus BC is equal to 0. And this is the same thing as lambda minus trace of lambda plus determinant of A is equal to 0. So then that means that lambda is equal to minus trace trace divided by 2 plus or minus square root of trace squared divided by 4 minus the determinant. Okay, so what conditions do we want on the trace and the determinant so that this thing is satisfied? What do you think?
Stuff underneath the radical.
This is what?
Less than 0.
Is less than 0, okay, yes. Okay, but
That's positive.
we want this to be,
Positive.
we want this to be, so we want the trace to be positive, right? Okay, so need,
Oh, wait, no, negative. There's a negative sign in
We
front
need
of
a
it.
negative.
oh, negative,
Wouldn't
never
that
mind,
negative
negative.
sign be canceled out from the characteristic equation? The characteristic has negative trace A, and then you go to lambda equals minus B. B in this case would be negative trace of A, right?
Wait, I'm sorry, there's a minus negative trace, so this is a plus. Is that what you were saying?
Yeah.
Yeah, okay, so this, actually we want this to be positive. Right? Okay, and what else? What about the determinant?
Greater than,
Something less than 0.
Well, we want this thing to be complex, right?
so determining is greater than trace A squared over 4.
Okay, so the determinant of A should be more than trace A squared over 4. You know, I want to say that it should be enough for the determinant to be positive. There's a graph that shows you what happens for each combination of traces and determinants, and I think that if this is not satisfied, we can still have a repelling steady state. But at this point, I'm not sure exactly how to argue that. But anyway, I want to say that. Well. Yeah. All right. So anyway, let's look at the trace and the determinant in this particular case. I mean, we already know that the steady state has complex eigenvalues because it's a spiral, right? And we can already see from from here that it's a spiral. The only question is whether it's a stable spiral or an unstable spiral, right? And you can see from there that it's stable if the trace is negative, and it's unstable if the trace is positive. Okay, so I guess that's one way to put it. Okay, since we know that the steady state is a spiral, we only need to look at the trace of A to determine its stability. Okay. And the trace of A in this case is equal to A minus B over A plus B minus A plus B squared. So, the steady state is repelling if and only if the real part of the eigenvalues is bigger than 0, which is true if and only if the trace of the Jacobian is bigger than 0 from that over there. And this is equivalent to saying that a minus b over a plus b is bigger than a plus b squared. And it is the same thing as saying that a minus b is bigger than a plus b to the 3. Okay? You guys agree? Great. Now let's think, what combination of values, is there any combination of values, a and b, that satisfy that condition? You would think if you pick a value of a, and you subtract something, and if you add something to the 3, it's going to be a bigger number than this. But we want it to be the opposite, right? What is it, Krista?
Use fractions.
Reduce fractions?
Use fractions.
What do you mean fractions?
Like 1 over 2.
Like something less than 1.
Yeah.
Exactly, right. So if a is less than 1, right, then a to the 3 is less than a, right? So this is now coming in handy. We want a to be small, okay? So let's pick a to be small. And what about b? b is kind of not helping, right? Because we want this to be bigger, but this is subtracting b and this is adding it, right? So let's pick b to be what?
Smaller.
Even smaller than a, right? So think about it. Let's say that a is 1/2, right? And b is really, really, really tiny, okay? So a minus b is still more or less 1/2, right? And a plus b to the 3 is more like 1 over 8, which is smaller, right? So there you go. That's the thing we're looking for. Is so then. So choose a to be less than 1, for instance, 1/2, and b much more tiny than a. Okay? Then this condition is satisfied. Okay, great. So backtrack. If a and b satisfy that condition, the steady state is repelling. If the steady state is repelling, and we already found this region, this rectangular region that is kind of attracts those let solutions go for any value of a and b, right? Then when we put all together, we get a set of parameters which is guaranteed to have periodic solutions using the Poincare-Bendixon theorem. All right. Well, that was a little bit technical, but anyway. So what do you think? Questions? No questions?
So
Yes, Patrick.
we have b is very, very small,
Yes.
so it's almost 0.
Yes.
So the change that we made to the equation to make it like that
It's very tiny, right?
is very tiny. So
Yeah.
it's more or less like our original.
Yeah, you're absolutely right. It's more or less like the original system, yeah. Because the original system we started with had b equal to 0, right? So what we're asking now is that b is just tiny, right? It's not 0, but it's tiny. Because it's almost like we have the same system as before, but with that system you cannot make the rectangular region. But if you make it just a slightly bit different, then you're okay. All right? Yeah. Any other comments? No? All right, great, guys.